Okay, so this is how we're going to solve this using the second derivative test. But when we go to sketch it, we'll do the first derivative test as well. It makes sense to do your first derivative test, and when you have the second derivative, also look for concavity so you can find all of our inflection points. So we're going to find the coordinates of the local maximum and the local minimum and the point of inflection for this function. And we're going to use the second derivative to show their local maximums or local minimums. So first of all, we'll find the derivative. 3x squared minus 12. You can factor out a 3, make it equal to 0. X squared minus 4, which factors to a difference of squares. So x equals negative 2 and x equals 2 are possibilities for maximum mins or maybe a stationary point of inflection. Now, normally, with our first derivative test, we would put 2 on here, we'd put negative 2 and check the intervals where it's positive, negative. We're going to just hesitate right now and not do that because we're going to just use the second derivative test first. With our second derivative, the derivative is 6x, so it's equal to 0 when x is 0.
And for our final subtraction, we please now call all the grade 9 students down to the gym for assembly. Again, that all students in grade 9 classes down to the gym for assembly.
So there's 0. And if you plug in a number, a negative number, and the second derivative is 6x, well, obviously going to be negative. You plug in a positive number, it's going to be positive. Okay? So let's see, what does it have to be at negative 2? Negative 2, comma, we'd have negative 8 plus 24 is 16 plus 5 is 21. And we have the point 2, comma, that would be 8 minus 24 is negative 16 plus 5 is negative 11. Okay. So despite not doing the first derivative test to see where it's increasing and decreasing, we can say that negative 2, 21 is a local max because we know that f prime at negative 2 is equal to 0 and f double prime at negative 2 was less than 0. And the way to visualize this is if we think about where negative 2 is on our blue number line here, and if there is a place where we would have a stationary point, it would have to be a maximum because it's concave down. Similarly, we can now say that 2, negative 11 is a local min because f prime at 2 is equal to 0 and f double prime at 2 is greater than 0. And again here, that's what we would imagine. That's the second derivative test. Again, the second derivative test is not a test to tell where it's concave up and concave down. The second derivative test is another way of finding maximums and minimums. But usually, since you've learned the first derivative test first, and you know that if it's positive here, then negative here, then positive here, that it's obvious that they are maxes and mins. Okay? When you do the second derivative, you can also find your inflection point. Here it'll be 0, 5. And we know that that's an inflection point because it changes concavity at that point. Also because f prime of 0 is not equal to 0. So it's not also a local min or a local max. So that's using the second derivative to say whether they're maxes or mins. Now we have enough information. We can sketch this. Once we put on our blue points here, negative 221. I'm going to estimate that to be about 21, 2, 11. 2, negative 11 would be down there. Our inflection point is at 0, 5. And we know that it's concave down here, concave up afterwards. Looking at my original function to see if I could do our x-intercepts easily would be a matter of if I could factor that at all easily. Just at first glance, I'd say no. You can't factor it easily. So if you wanted to find these points, then you'd have to use your graphing calculator to find them.